So here is 67p. And obviously this had already been imported and scaled correctly and done all the things that we mentioned before to make sure the data is good. And at the moment, we have our it's in a Cartesian coordinate system, same as before. Basically, the measurements we're making on this is as if it was a body that was just sitting on the Earth's surface in front of you. So all the measurements made, with reference to the vertical plane and this horizontal plane. Right. So we go to our meshes and open them up, and I've already generated some attributes. So as before, we have our dip attribute, the azimuth attribute, and our coplanarity that helps us see variations on the surface and pull out any viscosities that we can see. In addition to this, we have the gravity field information. So we have gravity potential, so how strong the gravity is at any particular point. So you see we have areas where you've got relatively high gravity potential, so showing in bright colors, which is on the end here, because my interpretation, the way I think about this, is that the gravity is quite high there because there is a lot of material behind you. And you see it have this bit here where your gravity potential is quite low. It's because there's not much material, but also you've got sort of competing gravitational forces coming from the head and the body in this area that would so the head gravity is pulling you in this direction, the body gravity is pulling you in that direction. Tend to get low potential in here.
Sorry, just to curiosity, if you see in the small lobe and the cliff, which is 900 meter high, and you fall from that cliff, and because of the low gravity potential there, you will take something like 3 hours to arrive at the base.
That's a good example. I hadn't thought of it like that. But yes, it would take you a long time. It's certainly very, obviously very different to what we normally think about. Anyway, so we've got the gravity potential, but also we have a gravity field. So this gravity potential is obviously the strength of the gravity, and then we have a field with X, Y, and Z. So you would have to imagine these to be normal vectors or gravity vectors coming out of the surface. I don't have an effective way of displaying that at the moment, but that's something I will work on. It would be nice to see those as vectors sticking out of the surface. Maybe for next year's winter school, we can see that. So that's direction, but we can also, from the gravity field, these vectors, calculate the dip, and a dip vector and an azimuth vector. So what does that actually mean? So these values are, if you were to be standing on the surface, what orientation would your compass clinometer show? What orientation would your clinometer show as being horizontal? Or if you had sat a glass of water on the surface there, what orientation would the top of the water be, right? So it calculates us our local horizontal based on the calculated gravity field of the comet. Now, the gravity field is calculated in gravity. It takes a long time to run. huge amount of calculation involved in this. It involves taking every individual triangle in the mesh and comparing it to every other triangle and doing that in turn for every triangle. It takes, I left this overnight to run. I was going to do it for Phobos, and because the Phobos shape model is much bigger than this, and it was estimating it would have taken about 5 days to generate the model. So I obviously wasn't able to do that in time. So it's something that you do once, leave it to run, and then once it's done, you have the data. You don't have to run it again. But it's a CPU intensive process that will take time. Anyway, so now that's our local dip that we can use to compare to our other measurements. So let's have a look at a bit of analysis on Phobos. Just as we did before, we've got our coplanarity attribute, and this enables us to start to try and pull out some of those terrace features that Matteo talked about Phobos. And we can start to extract those or highlight them in a little bit more automated way. When you're dealing with coplanarity, there is a paper which covers. Oh, so okay, I'm just noticed a question pop up. Very good question here. How accurate is this gravity field in the shape of the body and method used? I think personally that this gravity modeling approach does need a lot more work. I think it's a good approximation. And I think it's a good enough approximation to do some initial studies. And it's a good enough approximation for the purpose of this demonstration. I would spend working on the gravity fields and testing it and comparing it to what you get from other gravity modeling packages and approaches. So I think it's good enough for this. I wouldn't think at the moment it's good enough for scientific publication, right? So I do know that there is a lot more work to be done on the gravity modeling, though I think it's something that is definitely worth pursuing. Also, how do you actually really compare it? Because we have, again, there's so much uncertainty involved with this. We've got a bulk density for the Comet, which Matteo mentioned earlier on, 0.8 grams per centimeter cubed. But how does that vary across the body? That's another thing to consider that's going to have an effect on the gravity distribution. So I think it's a good approximation, and it's a good enough for giving us a good idea of how this all works and fits together. Not ready for scientific publication. Right. Right, so we can start to pull out some values. So the published work on using coplanarity suggests that a good value to use as a cutoff to say something is planar. I think it's about a coplanarity value of 4.5. So we could actually bring this down and really start to pull out bits that appear in terms of coplanarity attributes are very planar. And as soon as you do that, you do start to see bits that really stand out as being, that is particularly flat. And there as well. So you get some good terraces being pulled out just by looking at the coplanarity data. We can use that. We can use that if we go to on a different stereo net. So VRGS has two different stereo nets. There's the one here, which is the stereo net, and then we have this one, stereo net window. Might look similar. The difference is this one direct to your 3D view. It enables you to, as you're doing interpretations, you can see what's happening with your interpretations and watch your stereo net and your distributions build up with time. The stereo net window is designed for doing sort of a more detailed analysis and working with larger amounts of data, and it does give you a more control. It is also, it's not tied to the 3D. Just demonstrate that. If I were to go onto here and say, let's take a measurement there, measure an orientation, automatically appears in the tab, but doesn't appear on the stereo net here. If I want it to appear in the stereo net, I have to give the stereo net focus and switch it on manually. That means I have more control over this, an independent sort of view of the data. As well as that, if your mesh has a dip and an azimuth attribute associated with it, we can actually plot the entire mesh, the distribution of all the triangles on the surface on the stereo net. So we do that by a stereo net window gone. There we go. I do that with the stereo net window has focus. I switch on the mesh, and that's telling it, VRGS, to display the stereo net, the mesh on the stereo net. But to display it, we actually have to switch on to display that. And that is the overall view of the orientations on the surface of the mesh, of the 67p mesh. What this is telling us is, if I switch that on and let's do solid fill and let's do a log scale. The contour that you see here is an intensity plot. And this is one of the planes that we've interpreted. But the plane, also on the stereo net, you can plot a thing called a pole, which is a vector that comes out 90 degrees from the plane and will appear as a point on your stereo net. So the pole to this stereo net would appear over here somewhere as a single point. Sorry, the pole to this plane. When you've got lots and lots of these poles, you can and what this is showing us is some areas we have very hard tested. That is in a particular orientation like that, we have a lot of planes, or that's a common orientation. And you can use that to start to see if there are any patterns within your data. So we've got a high point here. There's perhaps one here, maybe over here as well. We're starting to get a little bit of a bright patch. This bright bit here is actually the other edge of this patch here. So as you go off the stereo net one side, you come back on the other. So that's telling us that there are some common distribution, common orientations within this data. Well, let us pull out a few more bits of information from it. Right, the next thing we can do is, if I back on here, got the stereo net window has focus. We've got the mesh displayed on it, but I'm going to switch on in the stereo net view coplanarity. Now nothing will happen here because we're not displaying the coplanarity attribute, but I can use the coplanarity stereo net now. Sorry, this coplanarity histogram to start filtering the data. So I'm actually going to change my filter. So I was just making it change the filter so that flat areas just show up as very bright. What I'm going to do now is change the stereo-net. Sorry, change the filter to show color in the high areas. It's doing that on the 3D view because the stereo-net window is the moment. But I should have to just do it on this. No, I'd forgotten. I also have into coplanar and switch on. Will just not plot things that are outside that range. See, it's updated the color scale on that one now. So if I switch on use filter, you see how that's changed on the 3D view. So it's filtering out everything that's a low coplanarity and only showing patches of high coplanarity. So just the terraces or things that are flat. And then I should be able to, on this, I might just have to redisplay. The stereo-net has now changed. And it's just showing the distribution of orientations of the flat surfaces. And that distribution has now changed from what we saw earlier. Remember when we had the whole thing, we had a bright spot just here. And now with the high coplanarity values, we've got a bright spot here. And I think some of this is down to probably the orientation of this far side, this side of the comet, which doesn't seem to be quite as well imaged as the other parts. And then also there is some lot of low values, flat values down here, which are orientation. So I think that's causing some of these biases in the data.
Yes, actually, just to add this point, this shape model was the shape model that was done considering mainly the northern hemisphere of the comet. So the southern hemisphere has been roughly interpolated. So you have these more planes that are, I would say, more complanarity in the southern hemisphere. There are other shape models already alluded here that are more detailed in the southern part. Even if actually even in reality in the shape model we had a good coplanarity in any case in the southern hemisphere with respect to the northern one. Sorry, David, just
that's good, thank you. Yeah, all right, so I think that hopefully that's starting to show you that with a little bit of work and using the attributes, you can actually start to pull out quite a lot of useful information that you can then use to focus your further investigations. Let's finish off. Sorry, how much longer have we got left in this session? Okay, right. Let's finish off with looking at using the gravity field orientation data. Right, so I'm going to go back to my coplanarity attribute here. I'll switch off the filter and let's go back to charts, and we're going to do go back to the whole thing. Right, I'm going to just get this stereo-net out the way. One of the other interpretation modes that we've got is in the dip azimuth. So we've done 3 points. There are a few other different ones. There's one here called attributes. What this will do is when you click on a point, it will get the orientation information from the attributes. So if you and it will only do that if you have a dip and an azimuth attribute. It looks for those and will extract the dip and azimuth information for the point. So let's do that. I'm just going to go back to coplanarity. Plane focus patches. Use my annotation mode I did before. Here's our stereo net. Now I can just click on these bright patches and it will extract the orientation from them. If I do properties here, let's change the size of them to 100 so we can see them. And there they are. Again, we hold down the shift key to return to move mode, navigation mode, to call it. And we can just go and add in lots of measures. Now you could also do this, possibility of this in a more automated way. There we go. We're starting to pull out, measure very quickly all of these orientations, and there they are in our charts window. But those are the orientations that are directly in the Cartesian coordinate system. We want to be able to look at those orientations relative to the local gravity field, to the local horizontal. And there is a way we can do that. It is a little bit of a workaround, but it involves, first of all, we need to change the name of these attributes. So I'm just going to put an underscore in front of them. Yeah, all right, so we'll just put an underscore in front of them. Then I'm going to change the name of my gravity field dip and azimuth. This is the orientation if you were standing on the surface that the horizontal would be relative, given in Cartesian coordinate system, the Cartesian coordinate system. So I'm going to change this to be dip and this is a gotcha. Got to remember to change that to azimuth, not azim. So now when I start to click points now, it will be pulling the orientation from the gravity field orientation rather than this from the surface orientation. So this means click the orientation point as that we can now compare to the orientation of the surface. Now the gravity field doesn't always match, the surface. So this would obviously be sloping if you were standing on the surface here. It can be quite confusing when you look at these gravity field values because you tend to think of them being in, compared to the Cartesian coordinate system. Means if standing on this here, that would be horizontal and you'd effectively be standing upright in this orientation and you'd be on a slope. That's how it would look to you if you were on the surface. So I can go and do that wherever I've made a measurement or anywhere else and actually start to look at the overall gravity field. We come around here, we see the orientation of these surfaces change. And again, we could go and compare, use those variations to compare what we see on the terraces, on those terrace surfaces, and see how they relate to what you might expect to form if they were related to the local gravity field. And I think we're nearly there time-wise, but just to quickly finish off and get some questions as well. It was about sort of looking at the bodies, the head and the body independently. And I was thinking about how might we go about doing this, particularly if you are using the StereoNet. The easiest way on something like this is we can just do a duplicate. I'm going to switch on my copy. I go into edit. I'm just going to do a rectangle select. So the head. And then we just go operations, delete selected. And now we can have a model of just the body. And then we could look at that in its own right and do the StereoNet analysis on that on its own. You could even, I think, with a little bit of effort, just coming into my head as I was doing this, tidy this up a bit, fill in that gap, and actually regenerate your easily regenerate your gravity profile just based on the lower part on the body, without the influence of the head. If you wanted to look at what was going on, potentially going on before the you know, if when there were separate bodies.